Welcome! Today we'll talk about integration by substitution with 4 objectives to find indefinite integrals. The first one is to use pattern recognition. The second one is to use a change of variables. The third one is to use the general power rule for integration. And the last one is to use a change of variables again, but this time to evaluate a definite integral. The first note will remind us of something we studied in the chapter on derivatives. It's the chain rule. F of g of x, if we take the derivative of that, is equal to f prime of g of x times the inside derivative. What we can do with this in integration is actually use it backwards. If we have an expression like this that we need to integrate, then the answer will look like that. So it's written here, the integral of f prime of g of x times g prime of x dx equals f of g of x, and of course plus c. So it's just the chain rule backward. What it means is it's going to be very useful and important to recognize when we have expressions that look like that. Here's a first example, and it actually looks like this. If we rewrite it, it's the integral of e to the 5x times 5 dx. This is f prime of g of x, and the inside derivative is 5. What is the original function we're looking for? It's e to the power of 5x. If I take the derivative of e to the power of 5x, indeed I get e to the 5x times the inside derivative. Here's another example, and right away as you'll grow more comfortable with this technique, you'll need to recognize we have x squared here, we have an x there. This x might well be the derivative of the x squared we have here. I mean, it's almost the derivative. What can we do to make it actually the derivative? We multiply by 2 and we divide by 2. So I haven't changed anything here. Multiplied by 1/2 and multiplied by 2. And now I see even better. 2x is the derivative of x squared plus 1. I need to change that a little bit further. Well, I'm extracting the 1/2. But now what I do is I multiply by 2 again and divide by 2 at the same time. So once again, I haven't changed anything, so that I really am in a situation where this is the derivative of my f function, and that is the inside derivative. The original function is x squared plus 1 squared all over 4. Now we can quickly check. If I take the derivative of that, x squared plus 1 squared, it's going to become 2 times x squared plus 1 times the inside derivative. Same thing here. We have an x squared plus 1. We can feel like the x that is outside will be the inside derivative. How should I change that? I multiply by 4 and divide by 4 in order to integrate this. I also multiply by 2 and divide by 2 to create this inside derivative. This explains why it's 1 over 8. It's actually 1 over 4 times 1 over 2. And now I'm in the situation where I can integrate. 1 over 8 times x squared plus 1 to the power of 4. The difference here in this new exercise is that I had limits, so we are integrating from 0 to 1. I'm not sure if this is the first time you see this style of writing. You can indeed, instead of having brackets on both sides, you can just draw a straight vertical line. It shows the limits of the integration. This is equal to 2 minus 1 over 8, which is 15 over 8. A change of variable is a more formal mathematical technique. You can completely rewrite the integral in terms of a new variable u before integrating. Here we are trying to integrate the square root of 2x minus 1. It seems pretty obvious that the change of variable is going to be u equals 2x minus 1. So we write integral of the square root of u. However, we need to be careful. I can't write dx because I'm now integrating in terms of u. So I have to check what is du. Du is 2 times dx, and that means dx is 1 over 2 du. So I'm going to change that. Instead of dx, I have 1 over 2 du. Now it's easy to integrate. And after simplifying, I can plug in x again, and I get 1 over 3 times 2x plus 1 to the power of 3 over 2 plus c. Same thing here, even though we may recognize that this is the inside derivative of some kind of sine function, we're going to do it formally with a change of variable. U equals 3x, therefore du equals 3 dx, which means dx equals 1 over 3 du. So it becomes sine squared u times cosine u times 1 over 3 du. Now we have to be careful of something. We had limits of integration, pi over 3 and pi over 2. But that was x equals pi over 3 and x equals pi over 2. So I need to make that change as well. I can't keep writing pi over 3 and pi over 2 because we are now working with a variable u. So when x equals pi over 2, what is u equal to? Well, u, it's written here, u is 3x. So when x equals pi over 2, u equals 3 pi over 2. When x equals pi over 3, u equals pi. So my new limits of integration are now 3 pi over 2 and pi. Here I recognize, it's easier to recognize that cosine u is the derivative of sine u or something like that, or power of sine u. It's going to be the inside derivative, and the answer is 1 over 9 sine cube u. I can substitute u equals 3 pi over 2 and u equals pi to find the answer. Many students actually find it easier to not make the change of variable for u as the limits of integration, and after they reach this step, they substitute u equals 3x in this expression here, and then, since they are using x again, they can use the original limits of integration, which are pi over 3 and pi over 2. That's totally fine with me, but some MCQ questions, for example, will require you to know how to change the limits of integration. One more example with a change of variable. We are going to set u equals root 2x minus 1. This example is pretty complex. It requires many changes. If u equals root 2x minus 1, it implies that u squared is 2x minus 1. We can differentiate and we get 2u du equals 2 dx, and therefore dx equals u du. But this is not enough for this expression because we still have an x at the numerator that we couldn't change. So we have to figure out from here that x is equal to u squared plus 1 over 2. X is u squared plus 1 over 2. Now for the limits of integration, x equals 1, x equals 5, it becomes u equals 1, u equals 3. I find that by substituting x equals 1 in this expression here. So making all these changes, I get this brand new integral. It's the integral from 1 to 3 of u squared plus 1 over 2 over u times u du. A huge step here. And the u cancel out, and now I have an expression that is much easier. I can break it down into 2 fraction u squared over 2 plus 1/2. That's easy to integrate. Once again here, you can, if you want, change u to root 2x minus 1 and then integrate from 1 to 5. If you've made the effort of writing the change a variable for the limits of integration, you can finish right now by plugging in u equals 3 and u equals 1, and the answer is 16 over 3. When you have even and odd functions, you can sometimes find integrals very easily, especially with odd functions. For example, sine of x is an odd function. When you take the fifth power, it's going to remain an odd function. So if we're integrating from 1 to -1, or from -1 to 1, or basically from negative a to a, the integral is always going to be 0. So the objectives again: use pattern recognition to find an indefinite integral, is this thing we saw where we use the chain rule backwards. Use a change of variables to find an indefinite integral. You set up u equals, for example here, 2x minus 1. The difficult thing is to know what the change of variable is going to be. In this particular example, it wouldn't be a surprise that someone would try u equals root 2x minus 1, and maybe it works, maybe it doesn't. If it doesn't work, it's okay. You just try again with another change of variable, like this one. Here we also used the general power rule. The integral of u to the power of 1/2 is 2 over 3 times u to the power of 3 over 2. Finally, use a change of variables to evaluate a definite integral. The big difference here is that we also need to change the limits of integration.